issues.
What's that?
With Zoom and stuff, it was complicated.
You know, last week?
No, like today, like less than an hour ago.
Class to shut out for like 15 minutes.
Probably just tired of talking to you guys. I don't know.
I'm doing pretty entertaining.
All right. So when I put this together, I get delta V equals minus the integral. I just put it all in there. When I take the dot product, though, what happens with r hat dot r hat? One. It's just one, right? It just becomes really simple. That's why this path is particularly nice. So I get 1 over 4 pi epsilon naught qs over r dr r squared, sorry. What does that give me? Oh, from RA to RB. Now, let's talk about minus signs since we talked about before. Let's assume this is positive. Because if you work it all out, assuming things are positive, then you put extra minus signs in, they take care of themselves. So assume this is positive. Are we walking away from it or towards it? Away. So if you walk away from a positive, what do you expect the potential to do? Just decrease. Right. So we expect the change in voltage or change in potential to be negative. All right, so we want to hold on to that.
What does that mean in words, though, if you have a negative change in potential?
It means that if your test charge is positive, right? Remember, U is Q of the observer. So if this was, if that means delta U, right? So that means if this is negative, that means that your positive, if this is a positive charge, it means you lost potential energy. But that means your kinetic energy goes up. You're gonna go faster, which makes sense, right? If these are all positive and you put a positive here and you let go, it's gonna speed up. It lowers potential energy, which means it gains kinetic. Yeah. If, on the other hand, it was a negative charge, that would actually mean what? Well, it would mean if this was negative and this was negative, this was positive, which would mean you gained potential energy, which would mean what about kinetic energy? If you gain potential, you lose kinetic. Well, that would make sense, because if this was negative and this is positive, it wants to go that way, which means if I'm moving the other way, I'm going to slow down.
Is that always the case, or does that assume it's a conservative system?
Great question, and yes. But in this course, we don't have friction. Yeah. So for us, we will not worry. We will have lossless situations, so we won't have energy leaking out due to friction. Yep. Isaac and Sydney, if we get cut off, because apparently it's been bad today, I'm recording this now, so I will post it. So don't panic if you get cut off. Okay, so let's do this. Do this integral. It's 1 over r squared integral. It's a power law. You have power law integrals. What do?
Plug it in.
Oh,
You take the 2, you divide, and subtract.
so you look at the exponent, look at the power, you add 1 to it, and divide by the new power. So this is a power of -2. I add 1 to it, so I end up with a -1 power. I have to divide by -1. Okay, those are all the minus signs. So I'm going to get minus 1 over 4 pi epsilon naught qs times this integral. I get minus 1 over r evaluate from RA to RB. And RA is smaller than RB. So that's going to be important when we figure out is this thing positive or negative. So this becomes QS over 4 pi epsilon naught, minus signs cancel there, 1 over RB minus QS S over 4 pi epsilon naught 1 over R A. Is that positive or negative?
Positive.
I don't know. Sure.
RA is small.
RA is smaller. What happens? So that means the denominator is smaller. What does that tell you about this fraction?
Small. It's bigger.
Really? Man, when I was a kid, I used to love to do that to my little baby brother. It's like, oh, do you want a half of a candy bar or a third of a candy bar? Go for the 3 every time.
So what you're saying is you're a bad older brother.
Yeah, I don't deny that. So this term has a larger magnitude, but it's negative. So the overall difference is negative, which is what we expected. So we got it taken care of. And if it comes out backwards, you just do this. You reach in your pocket, pull out a minus sign when no one's looking, and you just do that. You should think it through, but ultimately that's what you kind of effectively do.
So if it was either a positive or negative source, the opposite of the charge, it would just have a overall minus sign.
So what happens is, if we work it out, assuming positives, we get our expression. Now, if one happened to be negative, just the number you plug in would be negative. It just takes care of itself. You don't
So
have
it
to,
just have an overall negative.
yeah, yep. Which would just reverse gains and losses by overall. If both these terms get flipped, then delta V gets flipped, which is what would happen if you go from positive to negative. So the minus signs, if you work it out for a positive charge, the minus signs will take care of themselves for the negatives. When in doubt, just look at it and say, well, am I walking towards it or away from it? It's a positive. Work it out for that. Okay, now this is delta V. So this is V of RB minus V of RA. So I have a function of RB minus a function of RA equals a function of RB minus a function of RA. So that's where it's tempting to just say, oh, V equals this. But you have to remember that there could be a constant shift that cancels when you subtract. So what you really know is that for any radius, it must be that V of R is equal to Q over 4 pi epsilon naught 1 over R, first power, it's different than electric fields, plus a constant. And in each problem, you're able to choose this constant once to make your problem as simple as possible. It's the same exact thing those of you in dynamics had today, right? Choosing the reference energy to be something. That's what we're doing here. So for point charges, we usually say V of infinity equals 0, which chooses C equals 0. That's usually what you do. If you do something other than that, it gets kind of gross. So dull. But for other shapes, you would choose something else. And just as with potential energy, the value of V is not really physical. It's differences in V that are actually physically measurable. All right. How's that? How do we feel on that? All right. So that's for a point charge. Let's talk about pointers. Actually, let's do an example.
So when you say for point charge is B of 0 equals, or B of infinity equals 0, you're saying that like that's a It's like an infinite wire or an infinite point kind of scenario, or is it like an interval from 0 to?
No, what I'm saying is, so remember, the physical things we measure are differences. So what we're really implicitly doing is we say, oh, well, we'll choose a point at infinity to be 0. Or equivalent to that is saying, oh, when we say that something has a certain potential, we will just declare, what we mean is it has a potential relative to infinity. So the difference in potential from infinity is that. That's really the better way to say it. That's what that means. Okay? Infinity is nice because you can hide all sorts of stuff at infinity and say, oh, well, we'll just imagine there's like something at infinity that makes the problem nice. And nobody's ever been there, so nobody can tell you you're wrong. Okay, let's imagine we have a hydrogen atom. Did we do this example? I don't think we did this example.
You have said hydrogen atom.
Did I? Okay. Well, we found the potential energy in a hydrogen atom. That's what we did. That's what we did. What do we get?
So with the last class.
15 volts, yeah. 3, whatever. Okay, so we won't do hydrogen. Well, all right, let's just do 2. This is 1. Let's do 2 charges. Let's see what happens. We'll say we've got 1 nanocoulomb charge here and minus 1 nanocoulomb charge here. And I want to know just pick a spot along the line between them. Let's find the point here. Let's say that this, let's put the origin here. This will be x equals 0. So we'll say this is at negative 1 millimeter. We'll say this is at positive 1 millimeter. And we'll say this is at, and I want to know what's V here at 0.5 millimeters. Why am I choosing weird units? Because I'm a jerk. That's that simple. Just love to see you guys sweat. So I want to know what is the potential right here. Now, I gave you the formula for a point charge. How do we handle more than just a point charge? Just treat it as 2 potentials separately and then add them. Yep. Working with electric potentials is easier than electric fields because it's a scalar. So there's no components that you have to worry about. It's easier in that sense. So just find the potential at this point relative to here, or coming from this one. Find the potential at this point relative to the other charge. Add the results. They're at plus or minus 1 millimeter, but the place I'm asking about is at plus 0.5 millimeters.
So when we do this, we have to integrate from the source to the
No, you could, right? You could write down the electric fields and integrate.
Yeah.
Or it's easier just use V.
Yeah, I know, but I just confused the order. Which one come first and which one come later? Like the source first or the observer first?
SO. So it's,
SO.
it's observer minus source.
Okay.
But it's not going to matter here because you're taking magnitudes because it's a scalar. So that's why it's easier. But it should be SO. So observer minus source. Should be, even though it doesn't matter. Okay. What are we doing? Feel like we know how to do it? Everybody who's stuck.
V is positive.
Doesn't matter because V is where the observer is and the potential is created by the sources. If I was asking you to find the potential energy, that's when you would need its charge. Sydney and Isaac, how are you doing?
Good so far, I think.
Isaac, you okay?
Doing all right.
All right. Okay, so write down, look at what epsilon is. Oh, 8.85 times 10 to the negative 12. Coulomb squared per Newton meter squared.
What's that again?
8.85 times 10 to the negative 12.
Doesn't even remember it.
But in theory, what's that?
Oh. Yeah. Could it be 2 in the numerator?
Yeah, and it'd be a 2 over 4 times.
Oh,
I saved like the very.
and that one.
8.4.
Okay. Some people are typing numbers, so I'll give you another second and then I'll do it. So I'm going to say that the potential is the potential coming from the negative, sorry, from the positive charge, plus the potential coming from the negative charge. So I'm just going to find them separately and then add the results. So this is going to be 1 over 4 pi epsilon naught. That's a common factor, so I'll just pull it out. It'll be the positive charge, which is 1 nanocoulomb. So I'm going to say that's 10 to the negative 9 coulombs divided by, it's 1 over r. So it's different than the electric field, which is r squared.
9 or 6?
Nano, 9. 6 is micro, would be negative 6 million. So negative 1 millimeter, but I want the distance. It's the magnitude of the relative vector. So this is going to be 1.5 millimeters. This is going to be 1.5 times 10 to the minus 3 meters. Okay. That's the potential coming from this charge. And over here, I have the potential from this one, which is negative, so I get a minus sign, and I get 10 to the negative 9 coulombs divided by this distance, which is just 0.5 millimeters. Notice, okay, so that's going to be 0.5 times 10 to the negative 3. Notice it's a scalar quantity, so there's no unit vector that you have to deal with. R hat SO, you don't have to deal with that. It's a scalar quantity. And so I can put a little. So that'll be 9 times 10 to the negative 9. Well, the 10 to the negative 9, to the positive 9, times the 10 to the negative 9 makes those go away. So get 9. And whatever you get. Type it all in.
Is the second term negative because there was a negative sign up front?
It's QS. Epsilon naught is 8.85 times 10 to the negative 12.
If you just multiply the little thing by k, so
We're going to be using epsilon naught more and more, though, so I don't want to write it that way. What do we get?
I got 8.992 times
10 to the 18?
Yeah.
That doesn't, that's not right.
I got negative 11,980.
That seems more plausible. All right, so let me write that as 3 halves, like Billy did, right? This is 1 half. That update everything to 2 thirds. That is 6 thirds. So I'm going to get 9 over 3, and I get times negative 4 times 10 to the 3. So I'm going to get 3. I'm going to get negative 12 times 10 to the third, negative 12,000 volts.
negative 1.19 times 10 to the 4.
Oh, so that's, yeah. All right. That's a lot of volts. So probably we're not going to be able to actually physically do that. I mean, 12,000, negative 12,000 volts. Okay. All right. So that's how it would work with explicit numbers. Okay. Let's do another one. Let me choose the geometry the same way. It's close to here for how much is that worth doing? I'm trying to think.
What's the units on that again?
What's volts? Volts.
Yeah.
Yeah. If you work it out in metric, it'll come out in volts. Well, sure. Why not? All right. So let's work out this one. So imagine I have this pattern. I have a positive charge, I have a negative charge, and let's say that this is at location d over 2 along the z-axis. We'll say this is down, we'll say this is the origin. And we're going to have this one down here at negative d over 2. Well, and what I would like to know, so this is like this will be the z-axis. So you can imagine there's like a 3D space around it. And what I would like to know is what is the electric potential out here at some random location R. That's kind of tricky. I mean, to write it out in general, but I'll kind of help you do that. So notice, if this is this is the origin in 3D, so this is my spherical distance, spherical radius vector, or spherical radius coordinate. So this would be, and this is the z-axis, so what do you call the angle down from the z-axis? Phi is what math people call it. Physics usually call it theta, actually. Phi is the polar, whatever. So this angle, we're going to call phi, matching what you did in math class. And what I've done in other courses, or other problems. All right, that's interesting. So let's go through this then. The more general, or the general formula then for V from a point charge would be 1 over 4 pi epsilon naught charge of the source charge over magnitude of RSO. That's the general formula. So in this one, this is where I want V. That's what I want, V of R. So my source charges are these two positive and negative charges. So I could say the potential V is the potential from the positive charge plus the potential from the negative charge. Yeah. And then, so I'll just take them in turn. The potential, when we're working on the positive charge, I'd say, well, RO, that's where I'm asking about the potential, where I'm making the measurement. So that's over here. That's just going to be R times R hat, sorry, R times R hat. Where R hat is the spherical radial vector. And RS, for the positive charge, is just going to be D over 2 times Z hat. So all I really need is the magnitude of RSO. And that is simply going to be, magnitude of that is just going to be the square root of R squared plus, sorry, I've got to take the difference. Take it back. It's going to be, let me not do that. RSO, the vector, is going to be RO minus RS. So it's R hat minus D over 2 Z hat. Question. R hat points radially away from the origin because it's the spherical radial unit vector. Z hat points along the Z axis. Are those perpendicular? Is R hat perpendicular to Z hat? No. If they're not perpendicular, so if they are perpendicular, what's their dot product? It would be 0, but since they're not perpendicular, the dot product is not 0. In fact, remember, if I have A dot B, the general formula is the magnitude of A times the magnitude of B times the cosine of the angle between them. That's the general definition of dot product. So in this case, what is r hat dot z hat? Well, what's the magnitude of r hat? Emphasis on the hat. 1, because it's a unit vector. Magnitude of z hat. 1. What's the cosine? And what's the angle between r hat and z hat? It just, but it's not 0, it's not 1, it's just some, this is some random points, you just get some random angle. So it is whatever it is. But it's not, unless this is along the, say, x-axis or something, it's just some random number. It's not 0, it's not 1. Okay? Okay, so we're going to need that. Because when I work out the magnitude of RSO, so that would be the square root of RSO dotted with itself, right? That's how we define the magnitude of any vectors. You take the dot product with itself, and then take the square root. This is the square root of RO minus RS dotted with RO minus RS. So what I'm wanting you to see, so a lot of times we work with perpendicular things and then it just looks like the Pythagorean theorem. But now these aren't, they're not perpendicular, and so that you're going to get cross terms. Okay, let's work that out. So that becomes square root of, you can distribute. So that becomes RO dot RO plus RS dot RS minus 2 RO dot RS. Just FOIL the dot product. Okay, so what does that equal? Well, so in order to work that out, I get that RSO has a magnitude of the square root of RO squared, magnitude is just R squared. RS squared is just going to be plus D over 2 squared. And then I have 2 RO RS. You take the dot product. So that's going to be RO, is going to be R times D over 2 times the cosine of phi with a minus sign. Like that. It's kind of gross. It's just what it is. If we work it out in Cartesian coordinates, I can assure you it's even grosser. Okay, now, so then I pull it all together and I get V from the positive charge. It's going to be 1 over 4 pi epsilon naught times QS, which I'm just calling Q, over the magnitude of RSO, which is all that crap. Now notice the 2's cancel, so I'll just go ahead and simplify that and I get a minus sign here. Sorry. Minus R times D times cosine of phi. or 5 azimuthal angle down from the z-axis. Okay? Is that, right, it's kind of gross, but that's just what it is.
What did the two cancel come from?
When you do the cross term, you get 2 times this dot product, but RS has a magnitude of D over 2. So there's a. Yep. All right, what about V minus, the negative charge? Holy cow, do we have to go through this whole process again? Not really, because first of all, the charge changes sign, so you just get a minus sign out front, because it's a negative charge. And also, everywhere we had a positive D before, it's just going to become a negative D. When you work out RSO, it's just you should put a minus sign. So everywhere you have D, make it minus D. Everything else is exactly the same.
What about your angle?
It'll take care of itself. Because we're expressing it, we're going to express it as R hat plus D over 2 Z hat. And the angle came from the unit vectors, not the coefficients. So it's taken care of. Because it's still R hat dot Z hat when you use a cross term, and that's the same. Because it's the same axis and the same radial vector, so it's the same angle between them. We just tweak the coefficient to have it to be whatever we need it to be. All right? So all you have to do is make that replacement, minus and minus becomes a plus, and we get 1 over 4 pi epsilon naught minus q over the square root of r squared plus d over 2 squared plus r d cosine phi. And then so I pull it all together, get my full answer. This is the exact answer. There's no approximation. This is the exact answer. Oh, what do we call this pattern where I have a positive and a negative charge equal charges? It is neutral, yeah, but we had a name for it. We calculated this for an electric field. It made you so sick, you felt like you were going to die. It was a dipole. Die is because it's got 2. All right, so 1 over 4 pi epsilon naught times q, and then we get this stuff, 1 over square root of r squared plus d over 2 squared minus r d cosine phi, that's equal angle, minus 1 over square root r squared plus d over 2 squared plus r d cosine phi. Question, Gabe? All right, so this one we worked out, and then I said the only effect is to replace d with minus d. That flips it, and the overall sign from q.
So if you don't pull out the q before pi epsilon, there's still a minus in between them. I wrote it both ways.
Well, yeah, it's just a scale. You just distribute it, so same rules as always. So, all right, so that's the full answer for the potential of a dipole. But you'll remember when we had the formula for the electric field, we zoomed out and we came up with an approximate formula. And we're going to do the same thing here. What's the way to do that? Yeah. Okay. So here's the thing. R is, if you're really, for R, much bigger than D. Okay, so that means the dipole is really small and you're really far away from it. Okay? At first glance, they kind of neutralize and you just get 0, but it won't be exactly 0, there'll be a little bit left over. And so what we can do is approximate this. So we can think of this as small, right? Because D is much smaller than R. So this whole thing is small. So I call that thing epsilon. No, this one I'll call this epsilon. And actually, a better way to do it is not quite that. The better way to do it is actually to factor out the common factor of R. So let me do that. So I'm going to take the limit. R is much bigger than D. And I get V is Q over 4 pi epsilon naught. I'm going to pull out a factor of R outside the square root, which means R squared on the inside. And I get 1 over square root, pull that out, I get 1 plus, and it's going to be D over R squared minus D over R times cosine of phi minus square root 1 plus D over 2R squared plus D over R cosine phi. Okay, now I'm going to do what I was suggesting before. I'm going to call this thing, if D is much smaller than R, then I'm just going to call this thing epsilon. Call this thing epsilon. And in fact, if D is bigger than R, this term is like small fraction squared. So actually this term is bigger than this one in magnitude, typically. Just because this is like D over R is small. So this is like small squared. That's just small at first, so you can ignore that one. Okay. And to do this, I use the Taylor series and say 1 over the square root of 1 plus epsilon is pretty darn close to 1 minus 1/2 epsilon. It's the first term in the Taylor series. Remember Taylor series, you take derivatives, that's where your half's coming from the power. And then you subtract, because you're making, if you grow epsilon, the denominator gets bigger, which makes it smaller. So there needs to be a minus sign. When you plug that in, you're going to get Q over 4 pi epsilon naught here, 1 over R. The first term is just 1, so that you subtract and they cancel. And then the first term, which survives, has you get a minus sign from here, and a minus sign from here. You get 2 decomposits. You get 1/2. You're going to get a D over R cosine phi. This term. Over here, you get as a plus sign. So you have 1 minus sign, 1 minus sign. Again, 2, you get a plus sign. So you get plus 1/2 D over R cosine phi. They're the same, so they double up. Double up, and I get the potential for a dipole for R much, much bigger than D. It's going to be Q, let's try to rewrite that. Well, I bet a good way to do that would be Q times D. Why would I regroup those together? Why would I move those together? No. Haven't we seen Q times D before? Yes. Yes. We did electric fields. It's exactly the same thing. Q times D was the dipole moment. Over 4 pi epsilon naught prefactor. You get a 1 over r squared here, and I get a cosine of phi. And I'm going to write cosine of phi. Remember that was z dot r hat, z hat dot r hat. But I can also write that as z hat dot r vector over magnitude, or over r. Just converting the unit vector to a radial vector. So then I can rewrite this as q d z hat time dotted with r vector over 4 pi epsilon naught r cubed. 2, I get 1 more from there. This thing, q times d times z hat, was the dipole moment vector p. Dipole moment vector that we had for an electric field. Whew. There you go. So that's what you get. What is going on there? Well, what would that look like? Well, here's the thing. If you were to graph this and look at level curves, so you would have your positive charge, you'd have your negative charge. If you were to plot level curves of this, what it actually looks like is the following. When you get really close to a point charge, you get these more or less circles. But then when you get away from it, they sort of become more oval, kind of oblong sorts of shape. And then, on the other hand, if you wanted the answer, if you wanted something along the midline, when phi is 90 degrees, when phi is 90 degrees, what's cosine of 90? 0. So that means it's actually, the potential you would get is 0, but a constant 0 all along the axis. Well, that's an equipotential, a level curve. Which you can think of as like a circle that goes off to infinity. It's like infinite radius. Huh. That's what you get when you plot this. Why would you expect this sort of shape for level curves of potential? Well, if v is constant along a direction, then remember the derivative, so the gradient of v would be perpendicular to an equipotential. Right? The gradient of v is perpendicular to the level curves, like in Calc 3. So that means the electric field should be perpendicular to these. So what you can do is kind of sketch in what a curve which is always perpendicular to the level curves would look like. So like, oh, I don't know, you might start here, you might go, oh, that's blue. You might go down. And then, so start here and kind of go down, and then perpendicular, and perpendicular, perpendicular. Okay, so it looked like that. What about a curve that kind of starts at kind of 45 degrees? It kind of starts and maybe go here, 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 here. And then this one would kind of go here, here, here. Making sure to always stay perpendicular to the equipotentials. Have we seen this kind of pattern before? What about this one? It goes here, it kind of gets kicked sideways a little bit, so it kind of goes down, crosses here, here, here. Have we seen this pattern before?
Yeah.
What is it? Yeah. So in fact, we get that. So what we see, shouldn't be too surprising, is that the electric field lines are perpendicular to equipotentials. So you go along paths where, in blue, where the voltage is constant or the potential is the same. These are the directions, these are the level curves of potential. By definition, then they're perpendicular to the gradient of the potential. But that means they're perpendicular to the electric field lines. So you can reconstruct field line patterns from measuring voltage at different points. On Thursday, we're going to do exactly that. So we're going to paint use metallic paint and make a dipole pattern with two charges, plus and minus, just hook it up to like a battery. And then we'll go around with a multimeter, like one of these, and measure the voltage at different locations, and you'll be able to map out the kind of blue curves. And then we'll reconstruct what the electric field should look like. That's the answer we'll get. Okay. So we're going to do exactly this. As before, you can get this. Let's use this form. One other thing. Do you guys remember for a dipole, for a point charge, the electric field was like 1 over r squared. For a dipole, what did we find like a month ago, 2 months ago? Do you remember what the electric field was for a dipole? It was like 1 over r cubed. All right? Well, notice, just you take this thing, take this formula, q d cosine theta over 4 pi epsilon naught r squared, work out the radial electric field. Well, that would be like minus d by dr, r hat, on v. When you take a radial derivative, what are you going to get? What power of r? R cubed. So it hangs together. If you go through, so we would actually get, in this case, the derivative is going to give me a minus 2. So I would get q d cosine theta over 2 pi epsilon naught r cubed times r hat. You could go back and take the expression we had before. You can compare this to what we had, and that's exactly the same electric field we found using point charges, just subtracting. So it's the same. And you might remember last time I just evaluated at special points that were kind of like along the x-axis or along the z-axis. I didn't do random points because it was too gross to do all the vector stuff. It's easier actually to work out this. I know it looks complicated, but this is actually easier for an arbitrary point now. I haven't made any assumptions. And then just take the gradient to get an arbitrary electric field at an arbitrary point.
Is it 4 pi or 2 pi?
When you take the derivative, you get a 2. So, all right. So, yeah, I won't worry about it. Okay. Let's take a 5-minute break.
How long was the 5-minute break?
5 minutes.
This will be very important when I'm designing a break.
Could be. I'm helping.
So it's like magnetic field is like relative to the frame of reference, right?
Yes. Yeah.
This sounds kind of like a conceptual more than real thing.
Well, you have to say what you think is what you mean by real. In a certain frame, there are forces which do not look like electric forces. So it's real. But by changing frames, you can change, it goes away. Yeah, you can make it all electric.
Right. So potential energy it can be like relative to the frame of reference too.
Yes. Yeah. Energy, just like electric and magnetic fields are relative to frame of reference, energy and momentum are relative to a frame of reference.
So like there is no absolute potential energy.
So what you would really say, you would put, it's actually more than that. But anyway, what you can do is you can put the potential. There's another thing called a vector potential, which we won't learn about this year.
All right.
But they're part of a 4 vector. And when you change reference frames, they mix. Just like space and time mix.
Oh.
It's exactly the same math, same transformation. So one person, yeah, it's the same exact. So in this one though, if I stand still, if you have charge, if I'm standing still and you go past me, then I see magnetic field.
Yeah, and I also see magnetic field too.
No.
Not on me.
So you would say, if you're carrying charge in your hand, you would say that charge is not moving.
Yeah.
So you see only electric.
Oh.
I stand here and see moving charge, so I see both electric and magnetic. So they mix. And it's actually the same as mixing of space and time caused by relativity. It's exactly the same.
So weird stuff.
It's okay. To make sense, we just have to make sure that your description of nature is consistent with my description, but not the same. So as long as I can take your answer and convert it into my answer, and my answer back to your answer, and if we convert everybody to your frame, you take my answer, convert it to yours, then it matches yours. But what I see doesn't have to be the same as what you see, because I'm only in one spot. I'm not in both spots, so there's no contradiction. We just have to make sure that if I look at what I see, and then you tell me what you see, and then I do the conversion, then they match. That's the only important thing. It gets weird. It gets really weird. Yeah. There are weird things like if I have a book going on this line past you. So there's a picture on the back. What actually happens is it will, the light from the back of it will be able to reach your eyes before the book has gotten halfway. So from you, it will look like it actually twists.
Wow.
And yeah, I mean, it's a small thing. You can't see it like this, but it's.
I have another question. It's like the magnetic field, right? It comes from, we know it comes from the electron moving.
Moving electrons.
Yeah, the moving charge. Was it introduced before or after relativity theory?
Before.
Before. Then why don't people just think it might be relative too?
What's that?
Then shouldn't people just realize at that point already that it is relative to the frame of reference?
No, that came much later. They realize that. But even there, the problem is, like you have a permanent magnet, like iron. Yeah. It's not moving, but the electrons are. But we can't go to that rest frame, right?
Yeah.
So you might as well, for us, it will always look like the electron, you can't move with them, so you can't make that go away.
Okay.
And so because of that, it makes sense to just always think of magnetic forces as real.
But before that, people already know that it's caused by moving charge. Before the
Yes.
Yes.
But for a long time, they thought they were separate. They thought there was magnetic and electric, and they were separate. Maxwell is the one who put them together. That was in 1870.
Mason, what'd you get on the one test?
Oh, it was, I said if I got 80, I got 62 or 3 or something. No, I don't think it is.
I didn't do it on the last quiz. I got 8.
She sent the one tomorrow has like nothing to upload work. It was just going to be filling the box. She had it right with the no time limit. I thought she learned her lesson. This is the only one I've gotten.
Okay. All right. Is that correct?
240.
Yeah, nice try. Nice try. Okay. So we found the electric potential for a dipole. Okay, so that's pretty simple. I mean, the derivation is complicated, but the formula is pretty simple. And the way we handled that was we just treated a configuration of charges like a bunch of point charges, and you just figured out their charge. You figured out their effect one by one and added the results. So that's kind of easy. So there's something I want to kind of emphasize though. And look at the stored energy. In a configuration of charges versus the potential energy of a test charge. All right. All right, guys. So there are kind of two notions of potential energy, and you would have had this in physics 1 when we talked about like gravity or something, but it just never came up because when we talked about potential energy of the Earth, we never worried about building the Earth. We just assumed it was there. But now we're going to be talking about moving charges around. So there's kind of two notions of potential energy. What we've had so far is the potential energy of a test charge, or like one extra point charge. Okay, that's what we've been talking about. So this one is what we've been calling the potential energy of an observer, or a point charge observer, times V coming from the source. Right, that's what we've been doing so far. Potential energy of a test charge. So that means you have some sources, forget how you got them, you have them. And then you bring in one charge to some place and you measure its potential energy. Right? That's just one point charge. It's a different thing to look at a pile of charge and say how much potential energy does it have in it. Okay, so this is like the potential energy of adding one more, versus the energy that's already there. So trying to think of a thermal analogy. Off the top of my head, this is kind of like going from this is like kind of like internal energy. And this one's going to end up being kind of more like enthalpy, where with enthalpy, it wasn't just the energy in it, you also had to make room for it. It's that extra bit of energy. It's a little bit like that. So this top one, is basically you imagine starting with nothing. And then build up the charges bit by bit. So you're not talking about just one point charge added at the end. You're talking about piece by piece, adding it up, and just adding up all the energy you get bit by bit. And so, for example, when you talk about the energy in a capacitor, so the idea is then going to be that you build up all the charge on this capacitor, and then you want to know that energy. That's different than the energy of the last electron added. We're talking about the energy of the whole pile of electrons. So that's what we need to do. That's the energy stored in this cloud. So yeah. How do I do that? Well, yeah, I guess I'll just like that. So there's just two notions, I guess. The first question, do you understand the difference that I'm trying to get at? So in this case, imagine I have a whole bunch of charges here. To build this pile, I would have to add in energy each time I move a charge in. This one is a case where I have charges, and this would just tell me to add in QO. This is like the energy that QO has relative to these. That's one kind of energy. This is the energy just that's of the object that's sitting right there as you build it up. This is a little different. Right. So, the way we can figure this out, though, the difference would be so this is the one I want. So the idea is I start with no charge and I move one in from infinity. That's for free because it's nothing there, so it's easy. I can move it in for free. It's not working against anything. The push against. Okay, so the first charge is for free. QS1, let's say. Now, if I want to move another charge in from infinity to some position, well, that would require adding an amount of energy given by Q S1, S2. Or sorry, U S1, S2. Like, so that would be K QS1, QS2 over R 1, 2. You have to add that to bring, given that you started with, the first one was easy for free to add, then I add this one, that's the amount of potential energy you have stored up. Now you bring in another charge. Oh, well, now I'm going to have to add in this will be QS3. This one's going to push against both of the ones that were already there. So I'm going to have K, QS1, QS3 over R 1, 3 plus K, QS2, QS3 over R 1, 2, 3. Do another one. Now I move in another charge, QS4. So the energy that I would have now added, if I build this up bit by bit by bit, oh Jesus. QS1, QS4, R14 plus, because it pushes against everybody who was already there. So QS2, QS4 over R24 plus K, QS3, QS4 over R34. So the first one charge is for free, nothing. Two charges meant it pushed against one thing, so there's one term. When I have three charges, the third one pushes against two charges, so I get two terms. And then I get three terms for the fourth one. For the fifth one, I have five terms. It grows and grows and grows. So I can write this down in general. This would equal K, and I would have the sum over I. Let's say I have n charges total, or n charges. I equals 1 minus 1, right? Yeah, 1 to n. And then this one would be the sum over j from 1 to I minus 1. QS1, I'm sorry, I, QSJ over RIJ. Because what this is saying is you add charges and then you only push against the ones that are already there. So that means you're going to get 1, 2, and then you get 1, 3, and 2, 3. And then you get 1, 4, 2, 4, 3, 4. But you don't get 4, 4. You don't get So anyways, you kind of get, that's the pattern.
So this is for the stored.
This is the stored. We're gonna need this when we build up capacitors to write down the potential energy of the capacitor. Now, here's the thing. It's kind of a weird sum because this stops at whatever this is. That's kind of why it's weird. It turns out you can basically make it look symmetric by making both of them. You kind of double the sum and divide by 2. And so just write down terms you can show that this is true. So basically you can, what you can think of it is, it's as if you're building up these charges, and if you look at these terms, you can see that you're basically, you have nothing on the diagonals, and then you get something here, 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 whatever, on the upper triangular terms. So what you can do is basically fill in just double it, fill in the lower triangular one, so it just looks like you're summing over all the elements of the matrix. You have to divide by 2. That's kind of how you think of it. But there's a caveat. You have to, don't allow the diagonals, so I equals J. Because that would cause a problem, because you get a divide by 0.
So why is K over 2 now?
Into the sums. What this says is you sum over all the, actually I have the lower ones. So what this one says is you sum over all of the, I'm just enumerating terms like they're elements in a matrix. This means you sum over all of the rows from 1 to n, and then you sum over the columns from 1 to I minus to the diagonal. So basically, you don't include the diagonals, and you do the columns that are less than the row number. So that's like the lower half of the matrix. That's what the sum looks like. It's like you're summing over all the elements of a matrix, the lower diagonal, lower triangular part. And then you're just adding up all the entries. So what you can do, if you want to make this look a little bit nicer, is to double the matrix, count each term twice, and then divide by 2, and then it looks symmetric. So it just looks like a double integral. Okay. And when you do that, this, oh wait, but we've seen this. If I move K in here, and I move Q SI here, what does that look like? K QSI J over Rij. Looks like voltage. Yeah.
Good. Okay.
So the stored potential energy, like in a cloud of charge, is the sum over each bit of charge times the potential created by all of the other charges. And you get a half. So if I have a cloud, basically you can imagine, well, I don't know. That's what it means. That's how it is. And then basically you can imagine, well, how do I start on that? I think that's all. Basically, we can call this the potential at SI. And so you can think of this as 1/2, when we go to make these integrals, the integral dq v that's what's going to end up being. Okay. When you go to integrals, that's what we're going to have. Okay.
All right, so how do we apply that?
This one, I'll be honest, we will never use this brute force method. I just wanted to get to here. But what's going to happen when we get to capacitors, we want to talk about the energy stored in a capacitor to do circuitry. This is where the formulas that Tim, I'm trying to motivate, eventually I'm going to be able to show you where the formula Tim gave you came from. That's why.
And then we only need to know the formulas we already know.
That's what you're going to do. The point of the class, though, isn't to teach to the lowest common denominator. The purpose of the class is to enable you to do whatever you want to do. Right? So, right. Okay. All right. Now, so that's kind of general stuff. What we need to do now is kind of go through kind of a laundry list of different shapes and figure out the potential for a number of different shapes. So it's really going to be similar to what we had for electric fields, where we know the potential for a point charge. And if I have something that's not a point charge, I break it up into a whole bunch of little point charges, RS, RO, RSO, and then you're going to integrate over all the little point charges to add up the total potential that the sources create. It's going to be just like electric fields, but instead of vector quantities, you're integrating scalars. It's actually easier. But the logic is the same. So, for example, if we have a line of charge, actually, hold on, the line's probably not the one I want to start with. I don't want to start with a line. I'm going to start with a ring. A line is actually tricky. Line's actually not so nice to work out for a ring of charge. Okay, so I've got z-axis, and I've got the xy axis there. I'm going to say it has a radius r, capital R. It's a ring. How many dimensions is that space? 1D. If it's 1D, then what kind of charge density should I be talking about? Lambda, sigma, or rho? Lambda. Charge density lambda. Which should just be the total charge over 2 pi r. If it's uniform. And what I would want to do, or let's figure out the formula for the potential at this point along the z-axis. Okay. So we're going to treat it just like we did with electric fields, except we're not adding up little electric field vectors, we're adding up little bits of potential. So we're going to mark out a little segment of charge of length ds. How much charge is in this little baby step of arc length?
D theta.
Well, d theta is going to be related to ds. I can say that that's r d theta, but I want to know how much charge is in that little segment. I'd say it's just a little baby bit of charge, so I'd say dq, which is equal to lambda ds, which is lambda r d theta. Okay? So This is just like what we did in electric fields. And then I'm going to say, oh, well, it's like a little point charge. It's going to create a little bit of potential. So I'll call that dV, which is 1 over 4 pi epsilon naught times dq over RSO to the first power. And so therefore V is that integrated. It's basically what we did for electric fields, only now there's no unit vector, so it's easier. And it's just a first power, not second power. So all the skills that we had before carry over, copy paste basically. So for this situation, what's RO? Yeah, just easy hat. What's RS? Where's the source charge? Is there one? It's a whole bunch of source charges. It's a ring though. Is there any charge at the origin? No, so it can't be the origin. Like this guy right here.
The RDR?
No. What's the position vector for this little bit of charge?
It's all cos theta. Yeah.
It's exactly the same as what we did for electric fields. This part anyway. So work out the magnitude. RSO. But now it's different than the dipole example. These are all perpendicular because Z has perpendicular to X and Y. So that's just going to be square root of R squared plus Z squared. So I look at my integral. I know what dq is. I wrote it down. I just work this out. These are all constants. So I just throw it all in there and do the integral. dq is equal to lambda r d theta. And RSO is square root of Z squared plus R squared. Now I'm integrating around the circle. Is there anything? So here's the thing. When you set these integrals up, step one is just write it down. Don't rearrange it. On the test, you guys, the people who didn't do well, a lot of times they, I don't know what the heck, like people who didn't do well sometimes just wrote stuff down and then they just like pulling things in and out of the integrals without being careful, right? You gotta be careful. This is a correct formula. Start with the correct formula. Plug everything in without rearranging it. Then say, is something a constant or not? And then you can rearrange and pull the constants out. But do it in that order. Some of you guys started by rearranging and then writing the integral down. And then it's all wrong. Okay, so now, what am I integrating over here? Theta, right? That's the only thing with the D. Nothing else depends upon theta. So in this problem, that's why we do it first, everything is constant. And so you can pull it out. But that's just because of this shape. Other shapes, you gotta go slow. All right, so we're gonna pull out all the constants. All right, this is 1 over 4 pi epsilon naught lambda r over the square root of z squared plus r squared integral d theta from 0 to 2 pi. Then we do that integral, and that gives me a 2 pi. So this gives me 1 over 4 pi epsilon naught 2 pi r times lambda over square root of z squared plus r squared. This is just q. The charge on the whole ring.
Don't we just write that as Z plus R?
It's z plus r squared is z squared plus r squared plus 2rz. All right, so that's the potential you would feel relative to this ring at some point along the z-axis. How could you work out the z component of the electric field? How do you go from potential to electric field?
Gradient.
Minus the gradient. So use this to find the z component of the electric field. By symmetry, the x and y parts have to be 0. So how would you work out that? Remember, E is minus gradient on V, which means EZ is going to be minus the partial respect to Z on V. Let's do that. Because then it'll match the answer we found a month ago. Like on our next test, you'll definitely have these problems where you find the potential and then take the gradient to get the electric field. Definitely have problems like this. When I do it, I'm getting Q over 4 pi epsilon naught Z over Z squared plus R squared. These are 3 halves. And that you can check, that matches exactly what we found.
Don't you have to multiply by negative and half of that?
Yeah, and then there's a chain rule. So the minus sign goes away because the minus sign it's minus the gradient that gives you the electric field. So it's double negative. And then you have a chain rule, which gives you a 2z in the numerator, which cancels the half. So make sure you can do that. Give me a thumbs up if you're able to get that exact same derivative to work out. Okay, so that's right. Pull out the constants. q over 4 pi epsilon naught. Partial with respect to z, and I need minus the partial. I get a minus out front of 1 over this. So think about that as z squared plus r squared to the 1/2. Sorry, negative half. So it's a power law. So I have to take the derivative of the outer function and then take the derivative of the inner function using the chain rule. So that's going to give me, this part right here gives me, multiply by the old power, minus 1/2, times this thing to a 1 lower power, so z squared plus r squared to the negative 3/2, times the derivative on the inside, which is 2z. So this 2 goes away, and this minus sign goes away. The z's in the numerator, and I get 3/2 downstairs. Make sure you can do those partial derivatives. Let's do the potential of a ring, or sorry, of a disk. Potential of a disk. So same basic geometry, except it's solid now, not just a ring. Now it's solid. How many dimensions is that geometry? 1D, 2D, 3D? 2, because it's parameterized by a radius and a point on it's characterized by a radius and an angle. So I mark out a little bit of charge here. Okay. And I would say dq sigma times dA. In polar coordinates, what is dA?
R d theta. Wait,
R, D, R.
R d theta. Because it has to be, it's area, so you got 2 differentials there. It has to have units of length squared. Okay? And I want the potential here at some point z. Just go through it, right? So for this little bit of source charge right here, at location r and theta, RO is the same, z hat. RS is R cos theta x hat plus R sine theta y hat. It looks like before. The difference is on a disk, the radius isn't frozen. You want to eventually integrate over all radii, whereas on a ring, it was just frozen to be one fixed radius. So, and that's why I'm using lowercase instead of capital, just to help me remember. We'll do RSO z hat minus R cos theta x hat minus R sine theta y hat. The magnitude of RSO is going to be the square root of R squared plus Z squared. Just like all the others have done this. So I've got DQ, I've got RSO, got everything. So then I would say, okay, the potential is going to be the integral of 1 over 4 pi epsilon naught dq over RSO. I would write it down just like that, because it's guaranteed to be correct. If you want to pull the 4 pi epsilon naught out, fine. Don't pull anything else out. When in doubt, just write like that. And then put stuff in there, but don't rearrange it. Just like keep the integral as it is. Right? The problem that I think a lot of you guys have is you kind of write it down and you kind of shuffle things around and then put the integral in basically wherever it looks easy. But then the problem is it's just wrong. So you gotta put it down like that. Then the orders will be okay. So now I can pull out this constant. dq is going to be, so I get integral, it's going to be a double integral of sigma r dr d theta, that's dq, and RSO is here, that's going to be square root of r squared plus z squared. The theta integral goes from 0 to 2 pi, and the r integral goes from 0 to capital R. I would do the theta integral first, just give me a factor of 2 pi, pull it out, and I get 2 pi, sigma's constant, so I pull it out, 4 pi epsilon naught, that's 3 factor. And I get the integral of r dr, square root of r squared plus z squared from 0 to capital R. How will you do that integral? What kind is it? It's a u sub, yep. What is u going to be? Plus z squared. Do the pair. R squared plus z squared. Yep. So here, r dr over the square root of r squared plus z squared. Make u equal to r squared plus z squared. Du is 2r dr. From 0 to capital R. So this becomes integral du over half. R dr is half of du over u to the 1/2. And I integrate from u, when r is 0, u is z squared. And when r is big R squared, u is big R squared plus z squared. So that's just a power law integral. So you add the exponent, which makes it u to the plus half, divide by the new exponent, which is a half. So that's going to be u to the 1/2 evaluated between z squared and r squared plus z squared. So square root of r squared plus z squared minus square root of z squared. So now I just pull it together and get my answer. I can write it as, so I get 2 pi sigma 4 pi epsilon naught. Actually, I can go ahead and cancel the 2 pi. I'll just do that. Times. Times square root of r squared plus z squared minus square root of z squared. Screw that up. Yeah. It's not harder than what we did before. It's just more of the same. So if you understand what we did before with RS, RO, RSO, just turn the crank. Just cranking it out, one after another.
What is our other factor of an half been?
When you integrate, you add one to the exponent, so the new power is a half.
Yeah.
So you divide by half. It just cancels the prefactor of a half. Okay. From this, calculate the electric field in the z direction. Who needs help with the derivative? You can do it. Josh, you can do it. Mike, you okay? Gabe, how you doing? Okay. First thing is, what's a variable, what's a constant? Well, R is a constant, just the outer edge of the disk. So we're going to use this, which means the z component, we're taking a derivative of v with respect to z. So z is the only variable. Everything else is constant.
What I was throwing off on is, the last question you had, lambda equals q over 2 pi r.
Yeah.
I don't know if there was some variation of that for this question.
Well, I mean,
Lambda be,
this is a 1D problem, so that's why you have lambda.
yeah,
Whereas here's a 2D, so it's just different.
yeah, I know, but like, what would that be in this question? That's not, does this question have one of those? Like, that lambda q type, q over 2 pi r, does it have?
I could write sigma as q, the total charge over the area. But I didn't. The reason I didn't is because when I worked out the electric field, I left it like this before. So by writing it this way, then when you take the derivative, your answer will match what we found before. But it means cosmetically, you can change that, but. So everything is a constant except z. So just take a derivative with respect to z. Then you should multiply by 2z. Alex, how's it going? No, that's just a constant. Right. Yeah, but do them one at a time. So that's going to be, you just lower it, so it becomes negative half. Multiply by half. And take the derivative inside, it's going to be 2z. So 2 and half are going to cancel. So what do you get for this version? 2z. No, because we're going to subtract 1. Take the derivative, so we subtract off. This is going to go minus half. So the derivative, so you're gonna get, so when we do this, I get constants are out front, sigma over 2 epsilon naught. This is this thing to the 1/2 power. So I get the old x multiplied by the old exponent. And I have to raise this to, I have to lower this power by 1. So this becomes 1 over the square root of r squared plus z squared, because it's negative 1/2 power, times the derivative of the inside, which is a 2z. And I have minus, and I'm going to get z over the square root of z squared. Just half cancels the 2. Okay. So Mason, we did the integral without a formula for v. It's just a u sub integral. And then I'm having people take the derivative to get back to e. And you can see that it matches the formula we had forever ago. Did you get that to work out?
Oh, it was missing a factor, because these are factors. So the 2's cancel.
Gosh, do it. Derivative, whatever. So this thing, oh wait, sorry, I forgot something, I was wrong. E is minus that derivative, which means I get an extra minus on D. Sorry.
Why do you keep the square root on the?
Why? Yeah.
I remember, I know, I don't remember, but I remember you said something.
So I drew this picture as if Z is positive. If I write it like this, and I'm very careful, it works if Z is positive or negative. Because look what happens. If Z is positive, this just becomes 1. But if Z is negative, it becomes minus 1. And think about it. If Z is positive, the electric field is up. But if Z is negative, the electric field should be down. So it has to change sign. Okay? So, for this, if you make capital R really, really, really big, compared to Z, look what happens to the electric field. It gets really simple. If R is much, much bigger than Z, then the electric field we find, well, if R is bigger than Z, this becomes very small, and this is all you have left. And then, so this becomes positive sigma over 2 epsilon naught times Z hat over the square root of Z squared. And then that's what we expect, right? Because then if R is big, it's not a disk anymore, it's actually an infinite, it's like an infinite sheet that fills the whole plane. And the electric field we expect to get is just a constant. And above the axis going that way and down below the axis going that way. So, and this thing is exactly the minus sign. So if Z is, it's not Z hat, just Z. Times Z hat, sorry. If Z is positive, and it goes upwards, this is just plus 1. If Z is negative, it goes downwards, this is minus 1. But the magnitude of the electric field, or an infinite sheet, sigma over 2 epsilon naught, which is what we're finding. That's the result we had. We did it once using kind of this calculus integrating. We found another way using Gauss's law. Now we're seeing the same answer with potentials. Okay? So we kind of have so kind of going back to our rectangle of pain and suffering, we have forces, we have electric fields, we have V, and we have U. You kind of go in all different ways. It always comes, it's all consistent, right? When you can go through it any way you want. So for some problems, you have to use the kind of RS, RO, RSO, add up all the little bits, and get what you get. For other ones, you want to use Gauss's law. For other problems, it's easier to find V and then work towards E. Or if the problem has to find V, maybe you start, if you can use Gauss's law, do it. Right? So if the question is find V, if it's a shape with lots of symmetry, first find E using Gauss's law and integrate to get to V. If it's not, then you have to do this method, which is kind of a mess. But it's no worse than the first way I taught you guys to find electric fields. Because you don't have the unit vectors. Yeah, it's the same skills. And we're going to have the same thing happen with magnetic fields. There's going to be a brute force way, which is exactly the same for magnetic fields, called Biot-Saval's law. And then there will be a kind of a slick way using something called Ampere's law. Sometimes, like Gauss' law, sometimes it works, sometimes it doesn't. But if it works, you do that, because that's way better than doing it the hard way. Okay. That's what I wanted to cover today. So this is, so I think, sure, got them all. Yeah. I think these are the only two configurations for which we are going to use RS, RO, and brute force calculate electric potentials. Only these two. Other configurations, we're going to use some sort of symmetry trick, Gauss's law, something other way to do it. Because it turns out, so what's the example, the other shape that we did before for electric field that I haven't done? I started to do it and then didn't. A line. It turns out that a line is, it's not well defined. You actually get an infinite integral. And so when you calculate the potential, you actually calculate infinity. However, if you calculate the difference between any 2 points, the thing that's physically meaningful, you get infinity minus infinity, and it actually comes out to be the right answer. It's actually logarithm. So we're not going to do that one because it'd take a whole day to kind of justify it, and there's no point. So for a line, instead, if you had a line and you needed to figure out differences in potential, the way you would treat that is you would first use Gauss's law to get the electric field, and then integrate that to find delta V for a line. That's the way to do it. So in all of these,
So would that be two integrals then? You have to integrate first or the first field and the second field, that's basically.
well, what you would do is first use Gauss's law to get the electric field. So that's going to have a flux integral, but it's going to be easy. It's just going to be like for a line, it's just going to be lambda over 2 pi epsilon naught r. That would give you the electric field. And then you would say the difference in V is the integral of E dot ER. And it'll give you a logarithm, because it's a 1 over r integral. So in that one, you would, for a line of charge, we use Gauss's law to get the electric field and then work towards V. So basically, rather than just calculate here, we'll start here and then work our way that way.
So why you use little b for little r, because it was gonna be your variable.
Yep. So, okay. Anyways, so those are the two, a ring and a disc are really the ones that we do directly. The others, we're gonna use some sort of sleight of hand to get the answer. All right, so let's stop there for today. Next time, I can tell you what we're gonna do. We're gonna do parallel plate capacitors. They're easy, right? Because it's just constant electric fields, integrals. So if this is a constant, you integrate just in constant times delta x. Easy. So we're gonna get talk about parallel plate capacitors, define capacitance, and then we're gonna do two things. We're gonna have one part is we're gonna make a capacitor and measure epsilon naught from capacitance, and then the other thing we're gonna do is measure the equipotentials and reconstruct the electric field lines. So next class, hopefully we can do lots of hands-on things.
So homework due on Wednesday or Friday?
There's homework due on Friday on Gauss's law,
And then Wednesday.
Wednesday, Friday, Wednesday.
So when you say Gauss's law, is it gonna be similar to the quiz or Gauss's law, like what we were doing?
Quiz. No harder than quiz.
Okay.
If you can do the quiz, that's it. That's it. All right, I'll see you guys. Updates. I might have you too. Is that strong? I don't have duct tape, but I have shipping tape somewhere. That'd be better.
Couldn't get one from the drugstore, couldn't get one from the local supplier, so I had to go through Schultz and Nissan. Instead of paying
number 5.
Instead of paying $250 for it, I'm paying
Which one is it?
$470 for it, just because I have to go through Schultz.
Well, what type of car?
Oh, it's a 2017 Nissan Altima or
Go to the
Nissan.
Nissan dealership. They got colorful, I catch all the things up.
You can buy one for free, it just costs you your own plate.
Yeah, all the way down to the
Well, this kind of problem will show it's up on the front.
What's the name of it?
So
We get all the parts from any car.
there's charge and charge. And you want to know where possibly the field lines can be
I'm
zero.
not buying a bumper for my car, so I
You
got
can draw the field line pattern.
Rock Auto, huh? All right.
Anywhere in between is definitely good.
Yeah, and what happens is there's tons of electric field here. So it can't be here, can't be here. The only spot is right behind this guy. I might have the number wrong, but yeah, that right? So it's all about minus signs. So you kind of need to know that you're here. And that determines if you're standing here, this one was a negative charge, this one would be a positive charge. What that means is that the electric field from this guy is actually going to the right. When I stand here, only when I stand here. And the electric field from this guy is going to the left.
Yeah.
And so that gets you, so then you work out as a function of x, the formula for the E of x, when you're over here, and by knowing that you're over here, it tells you how to get the minus signs, gains and losses. And then you require it to be 0 and you solve for x. And you just add up the formula from 2-point charges, make sure they add up to 0.
That'll be on the final.
That kind of, yeah, point charges, find a place with potential 0. Yep. Or the electric field 0. Do the same thing for potential. Yeah. It'll be a different place though, just because remember the electric field is the slope of potential. So just because potential is 0 doesn't mean E is 0. E is 0. E is 0. They're separate. Related but separate. Saponic, I don't know. I don't know, so I'm gonna have, see a masking tape for that, I guess. Or you can use that
that
other.
one is strong.
I think so. Okay. Ah, here it is, here it is. Oh. Yep. What is
I
this?
just return it to Amazon. You know? Like it's a shin guard. For boxing,
Mm-hmm.
it's too small.